Welcome to Asymptotic Analysis using limits. In this video, we'll be using asymptotic analysis to explain why constants are ignored when using big O notation. So asymptotic analysis, what is it? Asymptotic analysis is an analysis method used to approximate functions that cannot be exactly calculated. If you've been watching the previous videos, we went over big O notation, and big O notation is just a way to represent the running time of a function based on the input size. If you take a step further back, asymptotic analysis is just big O notation, but it's just used to represent all mathematical functions. Big O notation is just a notation used to describe the running time of the algorithm. So let's get started. Before we get started, or before we explain why constants are not used to explain our running time, first we gotta know one definition, or this is the formal definition of big O notation. So the formal definition of big O notation is that the function f of n is equal to the big O of g of n if there exists positive constants c and k such that 0 is less than or equal to the function f of n, and f of n is less than or equal to the constant c times the function g of n for all n is greater than k. So what this essentially means that we have two functions, f of n and g of n. This part is just saying that f of n is always going to be less than c times g of n by a constant factor. And this k just means it's the point of where f of n and g of n are equal in terms of growth rate. And this whole definition is just a definition on why constants are not used to represent big O notation. So now we can move on to the calculus part of it. Before we start doing the calculus, we need to know one more definition, and that's how to calculate the growth rate, or how to define the growth rate between two functions. And to find that, we can just take the limit as n is approaching to infinity of one function over the other function, and this will give us the relative growth rate. So say for example, one of our functions is y equals to n, instead of x I'll call it n, and then the other function is just n times a constant factor. I'll just say it's 100, so it equals to 100n. So as you can see from the equations, y equals to 100n is just same as the first function, just times 100. So here we can call this f of n, and then this is going to be our g of n, and g of n is just 100 times f of n. So you can see where our c comes. This is our c. So to find the growth rate between two functions, we have this definition right here, the limit as n approaches infinity of f of n over g of n. And we can do this over here. Before I do that, let's take a step back and think about what the growth rate is. So let's say that let's do one more definition for growth rate. So growth rate is essentially just the limit as n is approaching infinity. And if we take the limit of a function over itself, this should just equal to 1. So the growth rate of a function relative to itself is 1. And if we do that over here with both of the functions, we'll get a limit as n is approaching infinity of, let's say f of n is n, and then g of n is 100n. And then if you remember from calculus, to find the limit of this, you can just cancel this out, and a limit of a constant is just a constant, so this will be the limit of 1 over 100. So what this is saying is that the limit as these two functions approach infinity equals 1 over 100, so that's our relative growth rate. And as you can see, this is a constant. And constants, it does not affect the growth rate, overall growth rate. If, let's say that we had two different functions, y equals n and y equals n squared. And then if we're trying to find a growth rate between these two functions, it would be n over n squared. And then this would just be 1 over n. And then this would just be 0. So you can see that there's a difference between two different growth rates of a function. This one of two linear functions, the growth rate is always going to be linear by some constant factor, which is that one right there. And then if you take two different functions that have a different growth rate, you'll get something other than a constant, which just means that the constant is not factored into a type of equation that's the same. So that's how you do it using calculus. Now I'll be doing it graphically on Desmos. Let me switch my camera around. Let me take that back. Let me switch this to here. Okay. And then let's put this down here. So here we have our Desmos graph. And a really easy way to explain asymptotic analysis using Desmos is with our x squared functions or our quadratic functions. Linear functions are a little harder to show, but they're essentially the same. These ones are just easier to visualize. So let's say we have two functions, y equals, or let's just say we have one function, y equals x squared, and then we have another function that's 2x squared. So you can see right here that it appears that x squared is growing, or 2x squared is growing faster than x squared. But if you zoom out to just like a really large number, you can see that these two lines are essentially just, the difference is so narrow you can't even see on the graph. And this is not even close to infinity. This is like 100,000. So just, you can see that if once you go to infinity, the constant factor doesn't really affect the growth rate of our function. And you can do this with any type of number. So let's just say, let's make one really wide. So we'll have 2,000. So here you can see that x squared, it has a much higher growth rate than 1 over 2,000 x squared. But if we keep going out towards infinity, that you can see that they look like they're about to come towards each other. And yeah, we have to scroll out a bit, but as you can see, once we're approaching infinity, these constants do not matter. The graphs look the same. And that's just how I want you to understand why constants don't affect our growth rates of a function. Thank you.